Okay, consider this to be a difficult problem. It's optional. Certainly, if you're taking the options, that's a good thing for you. But if not, don't worry about it. It's a difficult problem. I find them difficult too, by the way. So let's start it. And the thing I want to just go through is in review. And the review I want to just go through with you is something that we presented to you in the past. And let's just talk about that. And that's going to be this identity over here. And then I just, instead of using theta, I use z. And then what I did is that e to the minus iz. Let me go through that with you. So e to the minus iz would be equivalent to the cosine of minus z plus I sine of minus z. Again, I'm using this identity here. If you do that, e to the minus iz, using even odd identities, would be cosine of z minus I sine of z. All right, so that, not too bad. I got that over there. And then someone says, what are you doing next? Let me erase this over here. I'm going to kind of erase things one at a time. And I'm going to tell you what I'm going to concentrate on now. The two identities I just wrote down. And I'll just check them off for you. These two over here. And what I want to do is I want to subtract them. So I'm going to take e to the iz minus e to the minus iz. And what's nice about that, the cosines disappear. And what do you get? You would get 2I sine z. All right, now, of course, what I want to do is, let's see, what do I want to do there? I guess divide both sides by 2I. Let's put that down for you. So e to the iz minus e to the minus iz over 2I is the same thing as sine of z. Well, that looks awful familiar. I think I know what that is. That's just equal to I, right? So let's write that down. So e to the iz minus e to the minus iz over 2I is just equal to I. I'm going to clear the fraction by multiplying both sides by 2I. And you're going to get e to the iz minus e to the minus iz. And then you would get 2I squared. All right, multiplying both sides by 2I. And, you know, that's not too bad because it's just simply minus 2. But negative exponent sort of bothering me. So I'm going to multiply both sides by e to the iz. And you're going to get e to the, 2iz minus 1 equals minus 2e to the iz. And what do I get there? I guess I get e to the 2iz plus 2e to the iz plus, not plus, minus, sorry about that, minus 1 equals 0. And they're going to make a substitution because it looks quadratic in form. And the substitution is going to make it like u is equal to e to the iz. So you would get u squared plus 2u minus 1 equals 0. All right, so let me tell you where we got to. We're over here. And I think I can solve that. All right, so I'm going to get my eraser out. I'm kind of done, moving forward anyway. And I want to see if I can solve that. I can't solve it using finger numbers. And that's what's so problematic. I go the quadratic formula. And let me write that down for you. So let's see. U would be equal to, 2 minus 2 plus or minus the root. Again, we're solving this equation here. 4. And that's going to be minus a minus 4, which is plus 4. So you can get u equals minus 2 plus or minus the root of 8 over 2. And that's minus 2 plus or minus 2 root 2's over 2. So u is just going to be minus 1 plus or minus 2 root 2. All right? So I don't really want u. I want to know what z is. So let's take a look at this over here. So e to the iz is equal to, there's two things you can be equal to, right? I'm sorry, I made a mistake there. I just noticed it. When I divide 2 by 2, I get 1. So it's minus 1 plus or minus root 2. So I get two different answers. One of the answers I get is root 2 minus 1. The other answer I get is going to be, minus root 2 minus 1. That's a problem, isn't it? This here is greater than 0, and this one is less than 0. All right, so I'm going to go the easy one first, the positive root. So if e to the iz, the positive root would be root 2 minus 1. I could use natural logs now. And iz, it's running as a log problem. The natural log of root 2 minus 1. I would multiply both sides by minus I. And what do you get there? You would get z equals minus I natural log of root 2 minus 1. And let's see if we have that written down somewhere. I only got it written right over here. All right, let's just outline that. All right, led to that. We got z equals minus 1. Minus I times the natural log of root 2 minus 1. So I feel pretty comfortable about that. Let me get the other one. Less comfortable about that, by the way. I'm good with that. And let's talk about the other one now. And the other one is that negative problem. And let's write that one down. So what do you get? You get e to the iz is equal to minus root 2 minus 1 now. So we're going to factor out the minus 1. And the reason is I want to get a multiple of a positive number. So minus 1 times root 2 plus 1. And I can do logs now. All right, so what do you get? Iz equals the natural log of minus 1 plus the natural log of root 2 plus 1. And I'm going to multiply both sides by minus I again. I'll write that down for you. And you're going to get z equals minus I. Let's see what you get there. Natural log of minus 1 minus I natural log of root 2 plus 1. All right, things are shaping up somewhat. I still got a problem, by the way, that natural log of minus 1. And, sort of remembered, but I'll go through it anyway. But I'm going to write down that I kind of remember this, but we'll still go through it. It's going to be minus I, and this will just be pi I. This is minus I natural log root 2 plus 1. So z would equal, let's see, that's going to be, minus I squared, so just pi, and then minus I natural log of root 2 plus 1. All right, now I want to go through the how I got the log of minus 1 done. All right, so one thing I know about this thing, if I just think about what minus 1 looks like, minus 1 and a complex plane, let's see, this would be the real axis, this would be the imaginary, and minus 1 would be over here somewhere. Oh, I'm sorry, not minus, minus 1's over there. Oh, no, I'm sorry, it's minus 1's the real part, right? Let me erase that, made a mistake there. And let me start again. I get a real, an imaginary, and there is no imaginary part to minus 1. So if z equals minus 1, it's over here. So I know the argument theta is pi, and I know the multiple of I is 0. I know the length of that is going to be r, which is 1. All right, so I'm going to use an identity that we know about. And I notice there's a little error over here. I'll just write this down, that identity. That's r e to the I theta, and the r is 1, and that's what the r is. And I get e to the, let's see, pi, I pi, right? Because theta is pi. I'll correct that in the notes, by the way. And I know this is equal to minus 1. Again, this is equal to minus 1 over here. So minus 1 equals this over here. So take the natural log of both sides, right? And the natural log of e to the I pi is just I pi. And that's how we got that, all right? We got that right over here, all right? So we're done with that. And now that then comes, we got two solutions now, all right? Two different solutions. Let me just outline the solutions for you. This is one solution. All right, I derived that up here. Again, pi minus I, the natural log of 1 plus root 2 or root 2 plus 1. And the other solution we got was this one over here. We have two of them. However, you should start to realize what we're doing over here. Sine's a periodic function. And we're just going to add 2 pi k onto each of those solutions, by the way, with the understanding that k is some integer. All right, and that'll be our solution set. All right, so we're just taking each of those solutions and adding 2 pi k to it. Each solution adding 2 pi k to it. And that's the end. Thank you for listening. I do want to point out, if you do need to reach out to me, my name is Ron Bannon. My email address is Bannon, B as in boy, the @ symbol, NNON.US. Again, thanks for listening.